Tá, então, vamos aqui para a nossa segunda aula. A primeira aula a gente discutiu... Diga.
Short Portuguese.
Ah, desculpa, sorry, I forgot. It's jet lag. Yeah, so the first lecture we discussed some tools that we need to know, nucleosynthetic families, and many things. So now is the time where we're going to go use Gaia and other things to map the galaxy. And once we have this multidimensional map that we have discussed yesterday, then we can really play the game of galactic archaeology and learn about our galaxy. And in the third lecture, maybe we are already in the bulge, and let's see where we get. So this is the Gaia image. It's not an image. So it's the number count of stars. This is what you see there. Where is white, there's a lot of stars. Where is black, there's a lot of dust, so you don't see the stars. This is the early data release 3 from Gaia that was in December 2020. After this data release, there was the data release 3 of Gaia. But the early data release 3 is already containing most of the data set. What happened in data release 3 is that then we also got the spectra. Okay, so this is, the astrometry didn't change from Gaia EDR3 to DR3. And the DR3 was in 2022, June. Sorry, yeah. Okay, so this is beautiful because this is the image we see here when we are in the south. You see the Magellanic Clouds and the Milky Way. If you go, this image that I like to put in the entrance of my lectures. The Milky Way really on the sky. And, but we need to transform this map on the sky in what we want. What do we want? The three-dimensional map of the galaxy. We want to see in distance, right? And that is a lot of work to do. So what we need now, as we said yesterday, is to construct these 6D phase space maps, which means 3 positions, 3 velocities. Remember, if you have the position of stars and you can compute the distance, you have the luminosity of the star. So you have a lot of information when things are good. And then you add to this information chemistry, and you add to this information ages, once you can measure them. And again, if you have good luminosities, you also play in the game for age then. So in the last 10 years, there were 3 breakthroughs in galactic archaeology, not only Gaia. And that's what I want to briefly to explain to you now. And these breakthroughs are linked to the capability that we have to cover volume. For a long time, we were sitting around the sun. So you had the Hipparcos, which was the pre-Gaia mission, which gave very good results, astrometry and everything, for 100 parsec. Then we had some spectroscopic surveys covering up to 3 kiloparsecs. We need to extend to 10 kiloparsecs at least, when we are in the disk and the bulge. And so there are 3 things that have happened that has helped us in these last 10 years. And the first one is astroseismology of red giants. So sometimes you are used to astroseismology for planets. Astroseismology is the variation in the luminosity of the stars. There is, as you'll see in a while, the star pulsated, and you can learn from the internal structure of the star. And this doesn't happen only for sun, but it was discovered in 2009. This also works very well for red giants. And the point here for galactic archaeology is that if you have these pulsations, you can transform this information into mass and radius of the star. And which means if I have a giant, I can go very far away in the other side of the galaxy and have the mass and the radius of that star. And that's also a very good way to then get ages. Okay? So astroseismology of red giants was a breakthrough and give me precise distance and age for stars that are far away and in the field, because otherwise you need the cluster. But the cluster doesn't have the same age baseline, so you want a field stars for this job. The problem is that you have to rely to get the astroseismology from missions that are satellite missions, and these are Corot, was the first one, Kepler, K2, TESS, and there will be Plato. These are the missions. And these missions are not making the full galaxy as we would like, but are pencil beams. So in these directions, I'm gonna have very good data, for which I'm gonna have very good distance, and for which I'm gonna have ages. So that's important. The second breakthrough is, of course, Gaia. No? So Gaia is more precise than Hipparchus, we'll see in a while, cover a very big volume, go down to magnitude 20, measure almost 2 billion stars. So it's a difference. In the seismic missions, we are talking about thousands of stars. In the Gaia, we're talking about the billion of stars. No? And so this is also an amazing thing. However, Gaia astrometry, which means position and velocity, lacks the radial velocity. It gives me the tangential velocity based on proper motions that Gaia is going to measure, the proper motions. But I lack the radial velocity so that I can construct the full velocity and then get the orbit. How do I get the radial velocity? I need spectra. And so it's very important to follow up Gaia with spectroscopy. There is spectra from Gaia, which was in DR3, June 2022, but these are the RVS spectra from Gaia, come directly, but these are lower resolution and bright stars. If I want to go do galactic archaeology, I want to go fainter, I need to complement with other spectroscopic surveys. So the complementarity of the Gaia data is key, okay? Another way that I have to complement Gaia is with photometry, because if I don't have a spectroscopy and I have the parallax, I try to get the distance. And I can invert 1 over parallax only, as I said, for a volume of 1 kiloparsec. When I go beyond, then I have dust. I have other problems in the parallax. The parallax doesn't hold anymore your distance. You need more information. And the photometry will give you a way to break the degeneracy between I start getting redder because of the dust or because it's far away. And so the photometry in different bands will also help you. So Gaia is great, amazing, revolutionary, but needs complementary information. And that is a lot of work to do. You have to add photometry and add spectroscopy. And then the third, what I like to call this the third revolution, is apogee, because there were several spectroscopic surveys, and you'll see, but apogee has a special role in this story, because apogee is an near-infrared survey from Sloan, and it peers into the dust and brings us to see the bulge, and very close to the midplane. Before it was possible to see the bulge in spectroscopy, high resolution, mostly in the surroundings of whatever we call the bulge. And now apogee can give you a full view of the midplane of the galaxy up to the inner part of the galaxy. So that changed our view of the galaxy. These are the three revolutions. Okay, so why such a huge investment in galactic science, right? Let me just briefly comment on that, because very many times people say, but the Milky Way is just one galaxy. We have so many galaxies. But in the Milky Way is the only place, apart from some small galaxies nearby, for which we can get precise information of individual stars. So when you look to another galaxy, you get an integrated spectra, like the one that I guess was discussed by yesterday. So you have an integrated spectra, and you have to conclude the things about this population spectra. And for example, the mass, or the star formation, or the age. But that's you don't have the time machine, really. Here in the Milky Way, we have the time machine, because for each star, I have ages, and then I can go in time. So I can say, let's say I want to see the galaxy when the galaxy was in his first 2 billion years. I look to the oldest stars of the Milky Way, for example. You have to have good age. So this is why the galactic science investment in preparing spectroscopic surveys, going to follow up Gaia, is a huge investment, but pays off, because even if the Milky Way is not like all the galaxies, it has information that can be useful for constraining simulations and cosmological simulations about Milky Way-like galaxies and other kinds of galaxies. Okay, so let me just briefly tell you about the astroseismology of red giants. I'm going to focus on red giants, so not the ones that people are focusing for planets, okay? In 2016, these things were, it was discovered in 2009. In 2010, these things started becoming a big thing. And then every spectroscopic survey that was going on already at that time decided to follow up also the seismic targets. Because the seismic targets were holy grail, in the sense that seismology gives me a very precise gravity, much more precise than the one that comes from spectra. And so with this precision, I could put different spectroscopic surveys all in the same scale, which is very important. and also could get distance of very distant stars. So in this meeting, we put all the people together, people doing spectroscopy, seismology, to talk for the first time before Gaia. This is the first data set that had the full phase space information in some sense, okay? So what is seismology? So seismology is this variation in the photometry of the stars. You have to have very precise photometry, really precise photometry. That's why it's good for finding planets. And then you have this oscillation. And from this spectra of oscillations that you get from an observation, so this is one star, and you have a frequency, and you see the several peaks, like in a star. And I can get two parameters from seismology. One is we call delta nu, is the distance between two of these oscillation modes, or the nu max, which is the peak of the oscillations. Doesn't matter. This is doing seismology simpler and already give me a lot of results. I can do seismology in a much more complicated way, which involved individual frequencies, where people are modeling each of these modes, and then I can increase a lot of the precision I have in ages. However, to be able to do this, I need the time that a star was observed to be very long, like Kepler did. I need 1 year at least. And if the time I observe is short, the sequences of the variation is short, I lose information. So it's important to observe for a long time. That's why, from all the things I said, Corot, Kepler, and all these missions, the best one for this is Kepler. So for Kepler, we're going to arrive to more precision than for the others. So in some, we are working with these parameters, some we are working with more important parameters. So why is this a holy grail for us, for galactic archaeology? So this nu max and delta nu parameter that I show you, if you know the temperature, you can get immediately the mass and the radius of star. And this is amazing, because otherwise it's very difficult to get the mass and the radius of star unless you are in a binary system or you are nearby. But I'm talking about red giants. You can get this for very far away stars. And look, I can reach precision in distance of the order of 2 to 5%. I can get the gravity, as I told you, of the order of 0.03 dex. This is 1 order of magnitude better than any gravity somebody can get from a spectra, even if the spectra is high resolution. So this is a gift from nature, right? So we can get this. One of the reviews I suggest you to read is this review on Annual Review by Chaplin and Millian, where they talk about some of these things that were just coming out, so 2013. So here, for example, the impact of this astroseismology for red giants, I said, because you have this mass, you can reach up to 10% uncertainty and radius 3%. Now, this is what you measure with those scale relations I told you, but then you can transform this into masses, from masses to ages. For doing that is a model-dependent thing. For giants is good and is easier than for dwarfs, because for giants you have this relation. Mass and age is an almost linear relation here. So you can, if you know the mass precisely, you can infer the age. And here are some examples of some objects for which you know the age and you know the mass, and you fall in this relation. It depends on metallicity. So here I'm also showing the distance, how good the distance are to those stars that have seismology for different Corot, Kepler, and K2 missions. Most of these, because this works on the star has to be in a precise region of the red giant branch so that you get good parameters, so this whole machinery works. Most of them are brighter, and we are still sitting in a volume mostly around the 3 kiloparsec. But you have an important tail here that goes up to 8 kiloparsec. So imagine you can have stars going up to 8 kiloparsec for which you get an age. Amazing, this. And you get a very good distance. Here are some distance eclipsing binaries that show how good are the eclipsing binary distance with the seismology. These are calibrators to make people really believe the distance of seismology are up to 1%. In 2017, we wrote this paper here with more than 100 authors to try to convince the Plato to also put in their observation giants, because Plato is looking for planets and they only want to measure dwarfs because they want to find a planet in a sun-like star. But we Plato, it would be an amazing thing for galactic archaeology. So we put Plato, a galactic archaeology mission, in 2017 to try to enter these stars in the catalog. Until today, is a huge discussion if we manage, not managing, and so on. But we are going to have some, okay? That's what I can say here. So the first survey that we push for following up the target seismology was Corot and Apogee. And we built a sample called Corot-G, as creative as we can be. So the sun is here. This is the height above the mid-plane, above and below. And this is in X of the galaxy. The galactic center is here. As I said, in Corot, you had the two fields we used, 2 pencil beams. And you see, they are not choosing for galactic archaeology. They were choosing for planets. But one goes to the inner galaxy, but doesn't go to the bulge. Unfortunately, goes like this, past the side of the bulge, and they want to go to the outer galaxy. If I look from in X and Y, the galaxy, I see this cross here, 5 kiloparsecs. You see, doesn't go to the galaxy and goes here. So we use this sample here. For this sample, it was possible to get masses of 10%, radius of 3% uncertainty, and from there, do galactic archaeology with Corot. I'm going to show you later. After Corot, there was Kepler, which looks here above the plane. This is the Milky Way cartoon. So these are the 2 fields I was discussing before. And then Kepler is looking more to the upper field. And then Kepler broke and could not anymore look to that field and could look only to the ecliptic, became K2 mission. And the K2 mission added other fields, which are these gave me other line of sights, which for galactic archaeology was a given. But the K2 had not the same longer time series like Kepler. So what you can do with Kepler, you cannot do with K2. But with K2, you can get also good things because you have things on the disk that you do not have in Kepler. That's why I say, depending on what is your question, then you're going to use. So seismology and then impact, if I can summarize, is that you can 15 kiloparsec. You need to get the spectroscopic follow-up because you need the temperature to break degeneracies and to get this scale relation parameters better. And you need the metallicity to get better ages. Okay, so you need the spectroscopy information. And then you finally can get ages for giants, and then you lower your certainty in ages from giants, which is essentially 100%, because it's not possible to get isochron ages from giants, because the isochrons all go together in the giant branch, so you can tell if a star, the age of the star, and the isochrons separe, they diverge when you go to the main sequence, turn off, as I'm sure Sydney covered. The main sequence turn off, they diverge, and the subgiants. So there you can have isochron ages. But in the giants, not. But I want the giants, because I want to go far away, right? So we go from 100% uncertain, so we cannot do, to something like 30% if we use the normal seismology, delta nu max, with spectroscopy follow-up, and we can hope to get to 10% if we have the Kepler and the analysis of the individual oscillations. We made one science case where we took some stars in this paper, 2021, that came out in Nature Astronomy, where we pushed the precision of galactic archaeology to 10% and managed to give ages for the Gaia and Enceladus stars. So this is a revolution that's still happening. Second revolution then is the Gaia, of course, right? But I put here, Gaia, for me, in galactic archaeology, Gaia is a revolution per se in several fields. But for galactic archaeology, the revolution also starts when you complement the astrometry with photometry and spectroscopy. Without that, it's more difficult, okay? To organize, before Gaia, I organized a IAU symposium in Potsdam. This is the proceedings. Was just before the second data release of Gaia. There had been the first data release, which was still in a very small volume, and the Gaia DR2 was the big release. It was the first time we saw the 1.7 billion data set, right? And here, in the end of the conference, we were discussing the role of astroseismology to be combined with spectroscopic surveys, and how and if we were prepared to inject the Gaia data into all this mess. Because at that point, with seismology and spectroscopy, we already had so many things we were discussing. So then we made these two tables of debates, one about simulations. Here you have Ken Freeman, Julio Navarro, Françoise Combs, Wise, Francesca Matteucci. Here you have Beatriz, that she was in the panel, and the chair was the Simon White. And here the chair was Anthony Brown, which is the chair of the Gaia DPAC, the data analysis, and the people from data, so here Joss, Bia, and so on. That was very nice. Okay, so what then Gaia came out? So before Gaia you had Hipparchus, right? And essentially, in Hipparchus you had also very good accuracy in the astrometry, but essentially Gaia, this accuracy increased by a factor of 100. And you pass from, 100,000 stars to 2 billion stars. So that's the jump. And of course you had to be prepared, because this was really a headache when it came out, if I may say. Here is a slide that I took from Hobbs, where he is in the ESA voyage 2050. This was a call from the ESA, which is like the NASA in Europe, the ESA, for new missions. And we send a proposal for a Gaia infrared to be launched around 2040, okay? So as I said, not for me to use, but for you guys to use. And he's here defending our project in this discussion of which missions will be retained. For now, we are in the game for Gaia infrared. And that's Hobbs, who is the PI of the Gaia infrared. Okay, Gaia was launched in 2013, so 2023 was 10 years of Gaia measuring, okay? And amazing, so they made, so this was October last year, they made this cartoon calling attention for some things, so 1.8 billion stars, 10,000 papers, so you see how difficult it is to give talks nowadays about galactic archeology, because it's crazy. But some other interesting things, binary stars, there was a lot. There were black holes discovered, there were planets discovered, so it's really amazing. However, the goal of Gaia is an ambitious mission to chart the three-dimensional map of the Milky Way. That's the main goal. And that's the goal we are going to pursue in this talk here, okay? So how I'm going to use this data? We had to start prepare this before, of course, not to be caught in the last minute. Together with Basílio Santiago here from Brazil, I started a collaboration to build the spectrophotometric code using a Bayesian analysis, which I also saw that you already heard what a Bayesian analysis is, in order to use complement Gaia with more information and immediately try to extend and see for the first time the map of the Milky Way up to the bulge. That was my goal, okay? So we apply our code, our spectrophotometric code, first in spectroscopic surveys. For example, we were the first to produce distance for the Segue stars in Sloan, right, with the spectrophotometric code. And we were preparing this. After the code got the name of Star Horse, which was the name given by my ex-PhD students, two PhD students, Friedrich Anders and Anna Queiroz, who just finished as well the PhD. So essentially, what are we doing? We are taking photometry in several bands, Gaia, APAS, TILMAS, and also WISE in the infrared. Then we are taking the astrometry from Gaia, the positions and the parallax. Then we are taking spectroscopy input if we have. If we don't, we're going to use only photometry and Gaia. And in this way, we have two families of projects. One when you have, one when you don't have. And we were going to compare to evolutionary tracks. That's what the code, the Bayesian analysis will do. We'll try to use all these parameters and compare with data with stellar evolution tracks, gave us the most probable, the PDFs, the values of what we need to learn, which is essentially distance and extinction. As a subproduct of Star Horse, it can give you mass and age, but you don't trust unless it's in the subgiant and main sequence turnoff, and can give you also temperature and log G that the Star Horse considers the best. Because you can put an input of temperature and log G from a spectroscopic survey. Maybe there was a problem in that spectroscopic survey, but the Star Horse has so many other parameters. If the parallax was so good, the parallax telling, no, this temperature is wrong. According to this photometry and all this other information, this temperature is wrong. So Star Horse outputs the most probable temperature and the most probable log G as well, okay? So we made this, and there were in the literature also some other groups doing the same, but I have to say we were pretty successful and quick. In 2019, so the DR2, which was the second data release of Gaia, was 2018. In 2019, we already had this paper where we gave the photoastrometric distance, extinction, and astrophysical parameters for all the stars brighter than 18, which means that we already had a CMD here. Here I'm showing you a CMD, magnitude and color, absolute magnitude, corrected by extinction for 6 million stars up to magnitude 16, and 265 million stars up to magnitude 18. Of course, it gets less beautiful as you go fainter. You have more problems, you have less good parallax, and so on and so forth. But this was now it looks very easy. This was really a challenge to plot a CMD with 200 million stars and to do this. So once we were convincing our things is working, StarHorse is working. StarHorse now is a code that's much improved. Now it runs much faster. At that time, we had, of course, several problems. I had to convince the director to stop everybody's simulation in the computers because I want to use all the computers of the institute for a week. And then we had a problem. Then we had to use a second week. So we were not liked much during this time. But the result paid off. And we had a Gaia press release. So here is the people working in Gaia, Bailey Jones, were producing their distances based on another way to do it without complementary information. Because the idea of Gaia is like this. The insider from Gaia, they will publish and will validate their papers, and the idea was mostly only using Gaia. And the community can then use complementary information to improve that. That's the goal. It's a very nice idea, actually. So they using a 1/over parallax, but then also a sort of prior to extend that. Here you're seeing our galaxy, so the Gaia data of DR2 in X and Y. So like if you are seeing the galaxy from above, okay? And that's what you're seeing. And this is what we are seeing. There was a huge difference. We were seeing the bar in the density maps, which is beautiful, I have to tell you. Of course, we knew that the bar existed. And you can see it by masers and other subsamples that were already shown. But like this, in the density map, that you see the bar just coming out. Of course, in the beginning, we were worried. There are priors, there are things, there are systematics, and this is only possible to do for, this is the data set using only Gaia and photometry. We didn't have spectroscopy. And this data set was made public, and everybody then starts using this. And essentially, if you take this is what Gaia expects to cover the galaxy in the end of the mission, the simulation. And this is what our group already got after the second data release. So it was a very, very nice thing to have with some shortcuts, because there were some difficulties, especially when you are in the bulge where you have high extinction and your errors start increasing, showing you need spectroscopy. The idea was to show you need spectroscopy, right? Okay. So Gaia did a press release for us about this, the Milky Way bar. You can see we put our movie. So here's the galaxy seen from above with our data set. And then if you turn and look to as a side, you see that there is a missing piece here. This is towards the inner galaxy, and is the region full of dust, and Gaia is in the opticals, so you do not have that piece, okay? So that's essentially what that is showing. Then we wait for Gaia EDR3, which is the end of 2020. And during all this time, we are using this data set to prepare for MOST as well, which I will explain later in another lecture. So in 2021, we were ready with the next run of Gaia. What has happened between DR2 to DR3? The parallax improved by 20%, okay? So we had better parallax. But what really happened in Gaia from 2 to 3, EDR3, was an improvement in proper motion. Proper motion was very much improved. That's why this will be the sample that we are going to use to peer into the bulge, because even though the parallax is not helping me, the proper motion will do a great job in the bulge. That's why we wait for that to go into the bulge. So here we rerun this. This came out in 2022. Here is just a small list of improvements of what we did. And remind, all this was done during COVID time. So the little detail. Everybody isolated, we having to run huge files. So really, people work amazingly good, and we were 4 people, okay? So me, Ana Queiroz, who is Brazilian, came from the University of Rio Grande do Sul, made a PhD with me. She's now a postdoc. She finished PhD. She's now a postdoc at the IAC in Canada. And Friedrich Anders, who made the PhD with me before, he also spent some time in Brazil, 3 months. I sent him here in São Paulo. And he's now a senior postdoc in Barcelona, working with the Gaia group. He's inside Gaia now, too. And Arman Kalatian, that is a collaborator of myself inside the institute. He's a specialist in computer science and machine learning. So with Gaia EDR3, this is our map now, using our extinction that came in this paper. And we run this for 362 million stars. Essentially, we had an input of 400 million stars, 350 million converged. Of course, if you have disparate data sets, Star Horse cannot do anything. It doesn't converge. It's a good thing, you know? When it doesn't converge, that means trouble in the data. And then we have also flagged stars that have problems. So if you can work with the data, you can download it, or you can query this data. In the end of the paper, we always give some information how to query the data, and the data is public. And here again, you have our beautiful bar there, so it's confirmed. And again, you have the whole, because you don't cover, if you see the edge on galaxy, you don't cover the inner part. And here is where we hope to have one day Gaia near-infrared doing this part, okay? Hopefully. If you now do the three-dimensional galaxy, and let's just increase now 40 kiloparsec mapping. Now you have the galaxy, the barn, the Sagittarius, and the SMC and the LMC. When you have a bridge like that, is because there are uncertainties. So that the Bayesian probability distribution is including that distance, and so you have these pipes that appear, okay? Okay, so all these data sets are made public by us. We put in here in this website. Where is it? Did I put it here? I should. No, not here. It's in dataip.de. That's weird. Why didn't I write? I will write. And there we put some ideas of how to query some data, how to download some data, how to use some data. So our papers are very well received by the community, and a lot of people are using our distance. Okay, so that is mapping 3D, we got it, okay? Now, as I told you, with photometry and Gaia only, we have a lot of uncertainties. So we have to do better. And how we do better? Spectroscopy. And here is the work of Ana Queiroz. So Ana worked a lot on spectroscopy combined with Gaia, combined with photometry. And Ana was more concentrated. With Ana, we concentrate a lot in the bulge, as you're going to show in the last lecture, and the next lecture, because there you really need to peer the dust. And you need to do, the only way to get there and get orbits for stars in the bulge, which is amazing, is to get good Gaia, photometry, spectroscopy all together, and the Bayesian approach to bring you there. So essentially what Ana did, she was interested in the Apogee data release 17, because we were part of Sloan, so we could use this data. And of course, we run Star Horse for everything that was available in terms of spectroscopic surveys that were public. So here you have LaMost, low resolution, medium resolution, Apogee, which is a high resolution infrared, Gala, which is optical from the south in Australia, high resolution. Then you have Gaia ISO survey, the RAVE survey that was from my institute, low resolution, infrared, near infrared, and then the Sloan Segway data and the Gaia RVS data, because Gaia also produced in Gaia EDR3 some spectra, and in the beginning they didn't release the spectra in Gaia EDR3, but they released the input parameters obtained by the spectra with their own pipeline. Okay, so what Ana did, she combined all these spectroscopic surveys, and we got 11 million sources with spectroscopy, photometry, to do the job. Then use the parallax of EDR3, and we saw that all surveys have more than 10% objects, than 70% of the surveys with good parallax coverage. So it's amazing. It's really good. And the photometry we use here, Pan-STARRS, SkyMapper, 2MASS, All-WISE. All-WISE was and 2MASS, they are important to break the degeneracy because they are in the infrared. And then we use StarHorse, and we got the distance and extinction, and the other parameters I told you, temperature, log G, metallicity, and mass. The metallicity from StarHorse. And this is in the sky, all the surveys cover the whole sky then, okay? So when you do the mapping of the galaxy with this data set, precise distance, the distance here now are precise, of the order of 10% precision for this distance, you see one thing. Look the galaxy in X and Y, and you see the different spectroscopic surveys here, and this is where the bar is, and you see, obviously, that the only one really reaching the bar is apogee. This is why I say this is a revolution, because that's the data set we're going to use if we want to learn about the inner region of the disk and the bulge, which up to there was nobody knew, essentially. Okay? So apogee brings us to the third revolution. Apogee had another nice thing, because apogee started from the north, but then made a spectrograph, a copy of the spectrograph in the south. And that was key to add up points in the bulge area. And that's why DR17 became the data set that to use. Because you had then the apogee north and apogee south. These are the fields that they observe. This is the Kepler field here. And they also got a lot of data in the LMC, which also gave very nice results. Okay, so now I show you that it was possible to build a map of the Milky Way, different quality. So depending on your question, you decide if you want to use distance from photometry only and Gaia, distance from spectroscopy and photometry. So we started from this map, right? And here in this box, in the Anders et al. 2022, in this box you have something like 30 million objects. This is face on, this is edge on. So this square here, if I go to apogee, I go from 30 million to 30,000. That's the price you pay to have spectroscopy. Okay? So if you need a sample larger than that, you're going to use the photometry. That's why it depends on the question you want to answer. But let's go. We have here 30,000 stars, high resolution with good distance, sitting there. It's not a little. But among these 30,000 stars, there's a lot that are here in the interface between the bulge and the bar and the disk. And the density is a lot. So if I want a sample that's really sitting in the bulge, I can tell you we reduce our sample to 10,000. So that's the way, unfortunately, it is. Okay. So this first 40 minutes was to map the galaxy. Are you convinced that we could use the Gaia data quickly and efficiently, thanks to the StarHorse and the works a lot of Friedrich and Anna, who did their PhDs based on a lot of stuff that came from there. Okay, so now let's use all the information. We are armed with good information now. We have seismology when we need, we have photometry, we have spectroscopy, we are ready. What can we see? Let's look at the Milky Way thick and thin disk. First thing, if you go to a Galactic Archeology conference and you say, the thick disk is not enough. You're going to have to tell which thick disk. Because there is what we now see from this data, I'm going to show you the geometric thick disk, stars that are in thick disk orbit, so thick. But there is also the genuine thick disk, the high alpha thick disk, the really old thick disk. They are not the same, okay? So that's why I put here genuine or chemical. So you have to define. So this came out already before in 2008, and so it's something that I used to do what was then got to be known as a 2-info model of the Milky Way. This is a sample of 25 parsecs. Look the volume now, 25 parsecs, not kiloparsecs, parsecs around us. This is one of the most beautiful samples of this guy, Fuhrman, who did the 1 by 1 star and had the parallax and proper motion from Hipparchus. And he used his spectroscopic telescope and measured one by one. For these stars, he got very good ages. And what you see here is what we discussed yesterday, magnesium over iron versus iron up here. Here is the same plot, but inverted. Let's concentrate here up. What he has shown, stars that were sitting in 25 parsec. And why is this important? Because he had a volume completed. So this is a gold sample. The stars that were sitting here were very old, 11 to 12 gigayears. Stars that were in this sequence were the thin disk. And he did this cross here for what he called an intermediate population. Okay. Clearly, there was a chemical discontinuity, you see? You're not having something that does like this. You have a discontinuity here. And it was this discontinuity that I interpret as a discontinuity, meaning the star formation history of the thick and the thin disk was different. It's not that the thick disk evolved into the thin disk. It was two different events in our galaxy. The chemistry is telling you that, because otherwise you would have a continuum. But this is in 25 parsec, and okay, people say, okay, fine. This guy, one by one stars, continued doing this job, and then in 2021, published this new sample, because to increase these people here, and it's still the intermediate, what he's called intermediate, stay intermediate. You see that this is not a continuous thing. Of course, you say, oh, if he had colored this different, nah. But he has more information than what I'm showing you here, okay? And this is something that I now, working with others, they say, I'm convinced this is not the thick disk. And that's why this is the genuine thick disk, this is the thin disk, and this is this intermediate population. Here, he's now working 40 parsec. Okay. We had seen this already. If you plot abundance ratios, as I showed you before yesterday, in 2008, I was disturbed by this fact. If I plot magnesium over oxygen, they both are produced in the same channel, so they are flat, independent where the stars were formed. But what was bothering me is that there was a number of stars here, too metal-rich, because when you're running a chemical evolution model, which is these curves, you expect the final curve of the thin disk, which is the red one, should get to around the value of the interstellar medium today. So you cannot produce 10 times interstellar medium today, because you know the interstellar medium today abundance. So, but you had these very metal-rich stars. Beatrice Barb, we also had seen this around 2011, these super metal-rich stars here, and she has shown that they were not the youngest. Because in a chemical evolution model, you go and several generations are making material, so you believe that at the end point of your curve are the youngest, right? The last formed one, the most metal-rich. But it's not the case. She got, for this sample here, isochron ages, and they were intermediate old, okay? So, it was a very important paper, this one. Okay, nowadays, where we are? With the apogee data that I show you, with Gaia, with complementary photometry, here you have that same plot now, but for thousands of stars. And now here, I'm going to carry you to this. Here is, if you are in the galaxy, between 0 and 2 kiloparsecs from the galactic center. 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. So you're leaving the galaxy to the outer part. And here, each line is how up from the mid-plane you are. You are here very close to the mid-plane, below 0.5 kiloparsec, here between 0.5 and 1 kiloparsec, here between 1 and 2 kiloparsec. And here up is what Star Horse is giving me as precision for the distance and for the extinction, so that I trust what I'm seeing. And you're seeing something, right? It's not that there is a discontinuity, first you are seeing. We knew this already, but we didn't see this discontinuity extending to the inner part. You are seeing this, and you're seeing that this upper part here, the high alpha population, which is the oldest stars, are disappearing as you go out, you see? They are very less here. And you continue, because the data of apogee, you can continue. Now we are 10 to 12, 12 to 14, 14 to 16, 16 to 18, 18 to 20 kiloparsecs from the galactic center. What happened to the high alpha? Disappeared. First thing you're seeing. Second thing, the low alpha, the thin disk stars, the low alpha, they are showing up everywhere, even if I am a height above the mid-plane. Okay? So I'm high above the midplane and I'm seeing the low alpha. I should be seeing the thick disk, right? I'm high above the midplane. The thick disk, alpha high, disappeared. And the low alpha is there. How you interpret this? This also was highlighted, our result was highlighted here in this Sloan meeting by Marshall Bechardi, where he showed the before data that we had with Haydn, with the first apogee data before Gaia, and our extension of this up to 20 kiloparsecs, and essentially strike chemical duality, seeing up to the inner regions, including the bulge. This is a very important observation constraint. How you can interpret this? More or less, is in a cartoon. You have a thick disk, and you have the thin disk, and the disk is flaring. So this older part here is what we're calling really thick disk. The high alpha part stars are the thick disk. But the rest is just flaring of the thin disk. That's why I'm seeing the low alpha up there, you see? So that's why when you say the thick disk, I need to know if you are talking about the old part, what we call the genuine thick disk, or if you talk about the full disk, okay? So this is still being discussed. We're going to get back to this later. Finally, I wanted to enter a bit in the thin disk. Now, when I talk thin disk, I'm going to talk about low alphas, essentially, low alpha variety. So the things are disconnected, you saw. There is the high alpha and the low alpha everywhere. Let's talk about the low alpha population. Okay. So let me jump this part. Shit. I'll have to jump this part. Because this should come later. My goodness. Okay, here. This is what we have in our galaxy, iron and the galactocenter distance. Okay, this is the abundance gradient in our galaxy. These are now not the apogee data. These are the youngest stars in our galaxy, stars that for which I have age. The Cepheids, for example, we had discussed yesterday, right? The Cepheids, for example, I plotted here. Are those black points? And then other stars that are young, open clusters, young, are here. And if you plot the H2 regions, you also find this. So you have an abundance gradient in the Milky Way today, okay? And here, the blue points are the Corot stars, the stars from seismology for which I got ages, and I choose those that are younger than 1 gigayear. And what you see is that the Corot stars are on the top of the other stars. What means that the abundance gradient in the Milky Way exists and is kept up to 1 gigayear. It's not, the stars didn't move too much. But then you start going to the past, which is what you can go. You have other data sets now. You can use also, this is a data set new with Cepheids to trace the gradients. It's also beautiful because now the gradients, before I was showing you a gradient here, up to 6 kiloparsecs. You see, you're missing the 6 to 0. The data is not extending there. That's a problem of the data. That's why the apogee data is so beautiful, because it extends you. Now, if you go to more recent data, you have this amazing sample that's extending up to 3 kiloparsec here with Cepheids as well. And you still lack this data set here. It's the Masunaga paper. So this is how to trace the abundance gradient in the Milky Way. And then now you have also another sample of apogee who use clusters. These clusters are in X and Y. They are distributed like this. You see here the metallicity. You're already seeing the gradient here. This is more metal rich, this is more metal poor, and you can plot this also as a gradient here, and you see the apogee clusters. Maybe there is a flattening of the gradient here. Now here is going again from 5 to 18. Okay, so that's the last thing I'm going to show. Okay, so what did we do? And the model we're going to explain later. Essentially, this is the data set I was showing you, the gradient today. These are just concentrate here up because these are the observations. This is the gradient today. And now, with Corot, I have the ages of giant stars that are far away, right? The Corot G, Corot plus apogee. So now I can plot the stars between 1 and 2 gigayear, 2 and 4, 4 and 6, 6 and 10. And I see what? I see that by here, I don't have any more gradient. It's dispersed. By here, between 1 and 2, I still have something, but the scatter is really increased. Now, if I do a chemical evolution model, this line here is a chemical evolution model, right? And then I do a simulation where I paint the particles with this chemical evolution model, and I see how the radio migration is mixing them. In a simulation that is a cosmological one, zoom-in simulation, that's the problem. Simulations have some trouble to get the bar and everything. But just as an example, we do this, and these points here are how the stars will disperse from the gradient with time. So imagine the stars are born with a chemistry in a place. And then, due to radio migration, they migrate to another place. And they bring with them their chemistry. And that's what you're seeing here in this model. The gradient today, and now I trace the stars that were today here, back in time, and I see that they, if I go to old stars, they are scattered, and the gradient is destroyed. And now I mock this simulation exactly with the properties of the data, and in the middle row, I have what I will see in a simulation if I had the Corot data. This is what I would see, and it's very similar. So with that, we want to say that a lot of radio migration is happening in the disk, in the thin disk. You had the gradient, you see the gradient today, but if you go to old stars, the gradient is destroyed, okay? That's what they say. Now, you can see this in other data sets. You can take the same models that I show you, and you can use the clusters of apogee. Because now, the clusters are also points for which I have age and distance, okay? So I plot the clusters of apogee here, and I plotted our chemical and the models, and you see that in the beginning, the clusters and the model are matching the line, the gradient today. But then, if you go to the past, you see that the clusters are diverging from the line upper more than down, because they are traveling, the open clusters that survived, they are traveling from the inner parts of the galaxy outside. They migrate outside, therefore they survive. So the open cluster sample is biased, because the ones that survive are the ones that were traveling out from the region where they will be destroyed quickly. So this is beautiful as well. You can use another data set. That's the nice thing. Once you have a result, you check if this is happening in several data sets. So the last data set I want to show is this. Very recent. It's a paper we have in 2024, I think. Yeah. So this is, I'm using the OCAM survey, which is another data set of clusters measured with the NOTE telescope. And then, no, the OCAM is the apogee, sorry, is the apogee. And this is now our simulation in blue as well. And in the green, you have the gradients obtained with K2 data. Remember I told you the K2 were in several places? So we got the stars' ages and distance from seismology of K2 plus spectroscopic survey, and then plot here. It's a completely different data set, it's a completely different age, has nothing to do with clusters, these are field stars, and you've seen the same. You've seen the green, the K2 data is here, the green here is all up the curve, but as you go older, the green goes up. Meaning these field stars, for which I got ages, are also diverging in the same direction of the clusters for which I had ages. And in the same direction expected if this is happening due to radio migration. So that's why I say we are observing radio migration in the thin disk, okay? And I can do one more to be sure that's nothing wrong. Here we are using another data set, OCASO. Yeah, this is the OCASO survey, high resolution open clusters. And here we are plotting like this. The OCASO survey had open clusters younger than 1 gigayear, between 1 and 3, and older than 4. The same model, and what I see is a very important thing. Let's fix here 8 kiloparsecs, so where we are, our sun. And we can explain with radio migration a very intriguing result that people have been discussing. You see this cluster is at 8 kiloparsec. It's very metal-rich. This is an old cluster. It's more metal-rich than a younger cluster at the same position. How can you explain this? Because this cluster was formed here and migrate here. That's how we think we can explain this. So radio migration is happening. We see in the seismic data. We see in the cluster data. We see in the simulations that stars migrate. I didn't have to do anything in the simulation. The simulates just migrate stars, and we have to live with that. Now, this will let me do just one thing. So the ages I show up to now are ages are either on that I had the seismology in some pencil beams, or that I had, ages in the whole galaxy, right? Or that I had clusters, because clusters I have the age. But for field stars, it's very hard. So this map that I'm showing you is a map of the ages of the galaxy now in a bigger, from 2 to 16 kiloparsecs in the galactic height. And you're seeing here an age, much more imprecise age. This is an age now made using a machine learning method that is using the C/N ratio of apogee. So there's a lot of more complication. And is also using some important information from the Gaia data release 3, which is the XP spectra. It's a technical thing. So once you put all this back into a machine learning thing, is a paper by Anders and al. 2023, we see that after we have done this, and I was not believing this was working, we see that the thin disk is younger, and the stars that are above the midplane are tendentially older. But as you go out, you're seeing the flaring of the thin disk, just like we are thinking we are seeing from the abundance ratios. So you're seeing things that are the same. And final slide is this one. In a recent fire simulation, they are starting to look to abundance gradients variation in time. So here what they are plotting is the abundance gradient, which for our galaxy today is around minus 0.07 dex per kiloparsec. And here as a function of age. This is different data sets. Two of them is using our data, the one we did with K2 and the one we did with Apogee machine learning. These are these two curves here. This here and this here. The discussion now is this, that the people would like, in the Milky Way discussion, would like to think that the initial gradient of the disk, the thin disk, was very steep. And then with time, it flattened because of radio migration and so on. However, the simulations like the fire simulation have a gradient in the beginning, in the interstellar medium, that is flat. And then it steeps. Okay? Now, in chemical evolution, to start with a gradient steep or flat is an initial condition. You put by hand. And I know this because in 2001, I had a paper which is the abundance gradient, and I wanted to show this, so I had two models. One where the gradient flattens with time, and one of the gradients steepens with time, to show this is not something that the chemical evolution can tell you. You need this kind of simulation to tell you, and the data. But the data is difficult because I show you that the gradient gets flatter when you go to old stars. But what's the reason? Part of the reason is the radio migration. But maybe the interstellar medium was already flat, as the fire simulation shows. So this is where the debate is now. I mean, how can we constrain the oldest gradient in the interstellar medium of the oldest thin disk of the Milky Way, or of any galaxy, right? So these are fire simulations for Milky Way-like galaxies. The radio gradient today is steeper, more negative, for younger stars, which agrees with the Milky Way, although radio gradients are shallower in fire simulations. In the Milky Way, we have shown in our data sets that's also shallower, but we have interpreted and showed that radio migration plays a role too. That's the difficulty we have now, okay? So I wanted to finish here today because we have 1 hour. And if you want to ask something, I can go back to some transparency. Slides, sorry. Transparency is something from old people.
All right, thanks. All right. Plenty of time for questions.
Hi, Cristina. Thank you for the lecture. Can you go back, please, one slide? Yeah. What is the imprecision of the ages?
The precision of the ages is around 40%.
Okay.
It's bad, but it's okay. For the full galaxy, it's a great thing. right?
Sure.
But it's not for doing the job that I want to do, for example, dating the thick disk, dating the bulge. That will require 20% down to 10%. And that I can do with other data sets.
Okay, okay, thanks.
So how does the radial migration happen? Like, does it have to do with that pulsation that you showed in the
That I showed in the
simulations
first
yesterday?
lecture. So, also maybe. So essentially, is a secular process. And so is related to the interface between the bars, the resonance between the bar and the spiral arms. A lot of migration happened because of that. And you see, maybe if you come to the colloquium today, if I have time today, because I will prepare still, this is, for example, beautifully seen in a new data set that we have now with a high statistic, which is, thanks to Gaia DR3, which is metal-rich stars. So when you look into the guiding radius, so the guiding radius of, we have orbits for all stars now, and you have the guiding radius of the orbit, because the star can be passing here, but has an orbit, so the guiding radius is like the mean radius of the orbit. And so if you look to the guiding radius of the orbits of the stars, a function of metallicity, as you go more and more metal-rich, when you pass a certain value of metallicity, you see the 2 peaks or 3 peaks. You see that the metal-rich stars are linked to resonances of the non-resonance, the outer linear blind resonance, the resonance that you have between bar and disk. They are surfing in the resonance, the metal-rich stars. So these metal-rich, super metal-rich stars we have here came from the bar, came from the inner regions. It's a clear connection between radial migration and the interface between bar and spiral arms. However, other things can contribute to radial migration. Big mergers, I think, can trigger also some radial migration. That's why it's not a linear process that is able to model. You need to run an antibody simulation, hydrodynamic simulation. It has to be in a cosmological context. And that's why it's nice to see radial migration in the data set, to kind of have a feeling of how much is this. Because it's very difficult to constrain from first principles. And it depends a lot of the history of the galaxy and of its bar. The bar is also evolving during the time. So the bar changes with age as well.
So I had a curiosity about the bar. I mean, since it's a conveyor belt, like people used to say, right? It's like a track. Is it also very mixed in terms of the populations and the ages and metallicity of the stars? Yes.
Yeah, this is my next my last, depends, next lecture. Because with this data that I show you of apogee, you saw that I had made a square, probably. Wait a second, let's see if I find it. We can reach that, here, probably is here. Yeah, here. This square that I made here is that same plot. So here is this 4 kiloparsecs inside. So then what we're going to do in the paper dedicated to the bulge, we're going to zoom into here. We compute the orbits for our best stars. And when we do this, you can now, instead of, because the danger now in galactic archeology is that you have to say, who is thick this, who is thin this. That depends on how you select. This is very dangerous. So we do not select. What we do, we compute the orbits of these stars, throw it in an orbital diagram, Z-max eccentricity, and there you see the stars that are in bar-shaped orbits. When you look to those stars, what are their properties? You will see that they are totally mixed, as it should be, because the bar is not a stellar population. The bar is a structure constructed from whatever was there. And so if you had there young stars or old stars or somebody passing and got trapped in the bar, it should show. So this idea, which I think that our data contribute to change, that the stars on the bar are all metal-rich and all low alpha, is not the case. It's dominated by the metal-rich and low alpha. That's true, because a lot of the bar is made by inner thin disk stars. But, and also the fact that there are maybe gas flows enriching a lot of the inner parts of the galaxy. You see this. And so the bar has a lot of stellar populations, but it's true, it's dominated by very metal-rich stars. And that's why if you want to see the signature that those stars came from the bar here, if you look to the super metal-rich stars now here, you see this beautifully. And this is what is nice. But the supermeteor-rich stars are rare here. Beatrice found them here because she was looking for high proper motion stars. So she increased the probability to see them. But now, with the samples we have thousands of them we can see, thanks to Gaia.
Thanks for the lecture. Do you know if there's any group, anybody trying to run a simulation considering all these problems that you told now to see if we can model the formation of the galaxy?
He's sitting there. So yes. So I had a slide that I took out about the different kinds of modeling you have. I probably should find it here. So you have chemical evolution models, simplistic, with what we call instantaneous recycle approximation, meaning without this time scales of long restoring of chemical elements. So these work fine for oxygen, for example. And I'm sure here you saw some simple models for the mass-metallist relation. It works perfectly. It gives you the mean yield of whatever. So these are the simple models, very useful for extragalactic, where each galaxy is one point, okay? Here we are talking about the radial structure of the galaxy. So this is one thing. So these models are very good. Another model is like chemical evolution models without dynamics. Is also very useful to this the sort of models I did before, where you take into account the time scales of contribute, like we were talking yesterday, the different chemical families. This is another chemical evolution model pure. Another one is chemodynamical models, where you wanted to put the two things together, like we did. There you need a simulation that's going to give you the mixing of radial migration, and we paint the particles with a chemical evolution model. Why? Because at that point, 10 years ago, when we were doing this job, to show that there is radial migration, there was no cosmological simulation with good chemistry, because star formation is a problem. Star formation is an open problem, and there are subgrid physics. So we used a simulation that we trust. It was a cosmological simulation. It was a zoom-in simulation, because we need resolution, because we need a simulation with bar. And a lot of, if you don't do a zoom-in simulation in cosmology, many of them didn't have bar, especially 10 years ago. So now we are going to different families. There are people doing isolated galaxies with very high resolution, where you see the bar, and these are very useful to see these sort of problems, but it's not so useful in the sense that they are not in the cosmological scenario, and the cosmological things that are happening to the Milky Way, like gas accretion, mergers, and so, they impacted the history of the bar as well, because the bar can form, it's not a fixed thing, you see. It can have buckling, can have more than one buckling, so there's a lot of discussion, how many bucklings, one or not. Buckling is when you form the bar, and you form this X-shaped structure that we see. So this requires a different way, right, to do this. And then, so you need a simulation to form bar, which is not that easy, actually. The simulation, when you increase the resolution, sometimes the bar disappears. You get less and less bar. That's where we are, you see. Then what do we want? We want a simulation in the cosmological scenario that looks like the Milky Way, that has a bar like the Milky Way, and they have all the chemical elements. There isn't. So what we're going to do, we're going to bring results from galactic archaeology, Milky Way data, and simulations. That's what I'm going to do in the colloquium today. In the colloquium today, for example, I want to discuss the fact that we observed with data a lot of stars that are 12 to 13 giga-years old in thin disk orbits. That's the important thing. And that sparks a discussion, because disks need time to form in simulations, most of them. But that relates to the fact that also with JWST, we see all the disks already in place. And papers say, no, but this old disk is not the Milky Way. So this is going to be an elliptical gas. I don't know. But the fact is that here in the Milky Way, we also find that our thin disk has old stars. Are they from here? Are not? They probably came from the bulge. This is the discussion, because we don't have fully defined framework. We don't have a model that is so good that for which I can compare immediately my data sets. And we don't have a data set that is so good that I have all the information in a big volume. So the way to work is like this, like fragments. So you have a question, use this data set. Have another question, go to that data set. This is the art of this job right now. And you can do a paper per day if you have time, because the data is there, and the questions are there.
Hi. I was wondering about the observational part. Like you said, this is useful to also like know how other galaxies like has that properties and stuff. But I don't know. I want to know if we can like look at some galaxy, the stars in other galaxies. If we can do something like Gaia is doing here, but with stars in other galaxies, or we have only the light of the galaxy as a whole, and
Okay.
how can we make that,
Okay,
that
so
connection?
yeah, so this is, we have some nearby galaxies for which we have data of almost the quality of the Milky Way. Magellanic Clouds and some nearby dwarf galaxies. Then you have the nearby galaxies in the local volume for which you have the integrated spectra. That is the usual the surveys that I guess you already discussed, the manga and so on. This is nice because I can see the galaxy from outside. So I can see the bulge, I can see the inner ring. The picture I show you, for example, for JWST, I can see the gas, things that I am not using here. However, there, the spectra is integrated. And you're going to have to use a whole machinery to kind of give you an age distribution, a metallic distribution. But there you have other bias, because if this is integrated, the light is dominated by the youngest stars. And so it brings too much to the signal. So you need a lot of SEDs that you can break the degeneracy between. Or if these young stars are not there, then maybe it's extinction. So you need a lot of, so the technique is different. And so in this sense, in my opinion, it's a lot more difficult to do this job in another galaxy. Even if you're seeing the whole structure, depending on the question. But if you want that I trust the ages, for example, of integrated spectra, I don't trust the age too much, at least for the moments that we have right now. And we were in a whole, so we have, to answer your question, we do have data good as Milky Way for nearby galaxies. And we have another thing that's very nice, because I didn't have time to talk about this, are the galaxies that fell in our galaxy. This is amazing, because a galaxy like Gaia Enceladus collide with our galaxy 10 billion years ago. But we can find the stars from this galaxy here with chemistry and kinematics and age. And once we find these stars, this Gaia Enceladus is one example, we can trace the chemical history of this galaxy. I can give you the alpha over iron versus iron. I can look to the ages. I can look to the metallic distribution, like if I was doing the Milky Way. Another galaxy for which we have done a lot, Sagittarius dwarf galaxy. The Sagittarius dwarf galaxy was colliding with the Milky Way. The nucleus is there behind the bulge, but there are the streams left. And two of these streams pass here nearby. So just by using Starhorse, Gaia, and Segue, going deep, I got, for the first time, ages for the streams in Sagittarius. And the chemistry of Sagittarius as well. Here, the stars were sitting here, but they were for Sagittarius. If you look to the sky, they're all mixed, but now you have the integrals of motion. And for the things that are not completely phase mixed, so they didn't lose all this information, you can pick up candidates of Sagittarius, candidates of Gaia Enceladus. They stand out in these diagrams of integrals of motion, energy, angular momentum, and so on. And then you take them and you have chemistry and have everything for them. So you can then trace the history of another galaxy that is nowadays here. This is also, I find this amazing, beautiful. This was the first thing, this was the easy hanging fruits from Gaia, so many people run to that. I wanted to do the difficult part, which is mapping the disk and the bulge, and for the first time, seeing the effects of the stars coming here and so. But we also have a paper on the Sagittarius dwarf with Guilherme Limberg, who is a PhD student here at the University of São Paulo, which he could immediately select the candidates of Sagittarius. I do this because I need to validate my distances and to see if things are working and the ages. And so I said, here we have the segue data, low resolution, difficulties in the spectra, but go deeper. And I'm seeing in a plot a lot of old stars low alpha. I said, well, this should be Sagittarius or Gaia Enceladus. So I called Guilherme and said, have a look here. I am sure here you'll find Gaia Enceladus and Sagittarius. And he really rushed and got a paper very beautiful where he discussed the Gaia Enceladus and the Sagittarius. We got aids for the first time for Sagittarius stream like this. So it's really beautiful. Yeah.
Any more questions? If not, we can already break for the coffee break. All right, thanks, Cristina.
Thank you.
Again.